All right, our goal today is to finish this chapter, and then I will open the exam once we're done. You'll have till midnight Monday, next Monday, to do the exam. The exams are open book, open notes, but I want you to do it on your own. All the questions come from the slides, all the answers are there, so just read the slides carefully, and you should be good. All right, so we're on slide 14. There's 38 slides. I want to finish this lecture today. Okay. The Hoover Dam, the power Hoover Dam sort of when it's running sort of full force is 1.34. Well, you can think of it as 1 gigawatt. Giga is a billion watts. And what can you do with a gigawatt? So to run a house, a small house, you need in the US the average is about 1500 watts, but we'll say 1000 watts just to keep it. So with this thing, with the Hoover Dam, you can run 1 million homes, like 1 million small apartments. Okay, so that's what you can do. That's a large power plant. Okay. Now, this thing, if you build a solar power plant, it would cost you about $3 billion, $3 to $5 billion. Same thing with windmill. Nuclear power plants, we try to make them bulletproof and stuff like that. They run a little more expensive. Coal power plants are about 5 billion or something like that. Okay. So anyway, that's the kind of stuff that you need to be aware of. How many? Do you guys know how many of these are there in the U.S.? What do you need to run the U.S.? You need, so, we use energy in various forms and stuff like that. When you drive your car, you're using gasoline and stuff like that. These power plants are producing electricity for lighting, this running machines and all that kind of stuff. There is about 1,000 of these in the U.S. Okay? So there's 1,000 gigawatt plants producing electricity in the U.S. Okay? So I'm just giving you big numbers to give you the big picture. Okay. By the way, so here are some other interesting numbers. We talked about this before. To run you need 100 watts. That's 100 joules of energy per second. Yes, so you need the same energy as if to run these two bulbs. But here's the amazing part of it. Your brain needs 20 watts. Okay. That computer, that laptop needs 100 watts. And your brain is 1 million times more powerful than that.
That's the computer needs 100 watts to run, and the brain needs 20.
Mm-hmm. And your brain is...
The brain is more powerful.
100 million times more powerful, something like that, okay? I want it. Absolutely amazing. Okay? All right, here we saw that energy is the key constraint in rapid economic growth of a nation. If you don't have a regular, reliable, cheap source of energy, you're not going to grow. Okay. So better than an army, better than anything else, you want a cheap, reliable source of energy. Here's an amazing slide. So let's look at this carefully. A quad is 10 to the power of 18 joules. So this is the energy consumption in the US. This is 2018 numbers, but roughly the numbers haven't changed that much. I mean, now with AI, with all these supercomputers, data centers, that number will rise, but right now it's okay. So to run the US, we need 100 quads per year. This is how much energy we need to run the US per year. Okay. This shows you where the energy is coming from. Okay. So this is solar, nuclear, hydro, wind, and geothermal. These are renewable energy sources. What that means is, well, so these are renewable and these are fossil fuel sources. Okay. Let's add these numbers. That's 37 and 13, that's 50, 50, 80, roughly. See, about 80% of our energy comes from fossil fuel sources. Okay. 20 from renewable sources. So I want to shock the heck out of you. Okay. We spent $1 trillion in 2020 on energy. These are primary energy sources. Okay. When you use fossil fuels, what you do is you burn the fossil fuels, that's petroleum, gas, you're putting gas in your car. And for every $5 of gas you put in the car, how much do you get in motion? $1. What's happening to the $4? It's going out your, It's going out your tailpipe. Okay. So whenever you have to burn stuff and convert that to useful energy like electricity, motion, and stuff like that, you're about 20 to 30% efficient. Okay. If you're producing electricity using renewable source, if you're producing electricity, almost 100% of the electricity is used. So a Tesla is 90% efficient. My gas car is 20% efficient. Okay. So if you're producing the electricity not using coal, but if you're producing the electricity using solar and wind, that's a zero carbon footprint. Did you guys understand that? So hopefully, as you guys are, you'll all be driving electric cars. Let's hope. Yeah. And it'll happen sooner or later. But here's what the shocking number is. As long as we are using this, when you're burning stuff, that way of using energy is inefficient. So this is how much energy is going out the tailpipe, rejected energy. Out of the 100 quads, 70 quads is going out the tailpipe, folks. Out of $1 trillion that you spent on energy, $700 billion is going out the tailpipe. And besides, what else is happening? The worst crime. Forget this. What is the worst crime? You're putting CO2 in the atmosphere. So why do we do this way?
It's cheap.
Right now it's cheap. For this guy, all you have to do is pump it up from the ground, dig it up from the ground, pump it up from the ground. But thankfully now, solar and wind have gotten to be the cheapest. They're the cheapest source of.
And so you don't have to do anything with those, they're just outside.
Right. And not only that, see, businesses, what they like is, well, these prices can fluctuate. They don't like fluctuations. Okay? They want a steady input price. So businesses want predictability. All right, so you guys understand? So for every $10 with the current mix of energy, for every $10 in primary input, $7 is wasted in here. Okay. When you leave this room, I want you to be mad. What's that?
So a little mad.
Yeah.
More frustrated.
Yeah. No, but my point is, unless you understand the problem, you're not going to be able to solve it.
Horrible.
Okay, so you guys will have to figure this out. All right, now let's look at the numbers for the world. All right, so the US runs on 100 times 10 to the 8. The US uses 100 times 10 to the 100 quads per year. And the world runs on 600 times 10 to the 18 joules. Again, these are, again, 3, 4, or 5 years old numbers, but they still work. Okay. Now let's see let's put this in perspective. And today's 80% of the world's energy, whatever we said for the world is generally true for most countries. If you're a large enough country, it's true for that. So if you say something for the US, that's true for the world as well. Okay. And coal, natural gas, and oil, those are the 3 fossil fuels. Coal, natural gas, and oil. Okay. They make up more than 80%, but roughly 80% of the world's primary energy source. Yeah. Okay, so what we're going to show you is, so in the US, just for electricity, there's about 1,000 Hoover dams. But, okay. So if you account for everything, oil that you put in gas and stuff like that, what we're going to do is we're going to give you a number that shows you what is needed to run the world. Okay. So what this number is what this number says is a gigawatt is a large power plant. You can think of it as a Hoover dam. Has anybody been to the Hoover Dam here? Yeah. Okay, so that's a homework assignment for you guys before the semester is out. All right, so it's a large power plant. What this number says is to run the world, you need about 16 to 19,000 Hoover dams running all the time at full power. That's what's needed to run the world. Okay, that's what that means with our current mix of energy sources. You will learn that in a little bit, at least at the end of the chapters. So this is with the current energy mix, 80% fossil fuels. But if you ran the world entirely with solar and wind and renewable energy and nuclear energy, all you'll need is about 12,000 of these. Why do you need less?
Would you have other sources of renewable energy?
No. So if the world, so currently you need 19,000 with the present energy mix, 19,000 equivalent Hoover dams to run. But if you were running the world on renewable energies, all you would need is 12,000 Hoover dams. Why is that? Running the same world.
Oh, because it's more efficient?
Okay, put a little more meat on that bone.
There's not as much energy wasted?
Yes. So right now, this mix contains fossil fuels where 67% of the energy is wasted. You won't be wasting that, okay? When you produce electricity directly from solar and wind, electricity is 90% efficient. You can convert all that electric energy into whatever you want very efficiently. Like in a Tesla, the battery charge converts 90% of that electricity stored, that energy stored into motion. Whereas when you pump gas in your car, only 30% of that is converted to motion. So here is how the numbers work out. I'm just giving you. So this is the amount of energy needed to run the world in 1 year. And here is 1 year in seconds. Okay. Joules per second is watts. Okay. And if you divide that by the power of the Hoover Dam, that tells you how many Hoover Dams you need. Okay. So that's a good number to remember. You guys understand this? Okay. All right, so today 80% of the world's energy comes from fossil fuels. What are the fossil fuels? And
Natural
gas.
gas.
Yep, so 3 sources. And the problem with using those is the use of fossil fuels leads to increased CO2 levels in the atmosphere. And we'll see what that does. Okay. Okay, so the renewables contributing 20%, the fossil fuels contribute 80% today. What we want to do is, the ideal world would be, this goes to 0, and that goes to 100%. Okay? And that will happen by the end of this century. Okay, by 2100, that'll be true. But that's waiting it a little too long. Hopefully, it'll happen much faster than that. Okay. All right, so we use these sources of energy for energy. Why do we need energy? To do work, of course. The use of fossil fuel leads to CO2 in the atmosphere, which leads to climate change. Okay? So this is, I guess, politically not correct, but I mean, that's the truth. All right. So this leads to climate change. All right, so fossil fuels are hydrocarbons. They're molecules that have carbon and hydrogen in them. This is natural gas. Methane is natural gas. Okay, so here's motor oil, and you can see all of these are hydrocarbons. This is diesel fuel. This is gasoline. Gasoline, the major component of gasoline has 8 carbon atoms, so this is showing you 7, but anyway, that's sort of the octane rating, telling you how many of those 8 carbon atoms you have. Okay, so when you burn this thing, so when you burn a hydrocarbon, when you burn something, what is it that you're doing?
Breaking it apart.
When you burn something, you're combining it with oxygen. That's what it means. Okay? Why do you do that? Why do you burn? Huh? To get energy. Okay. Okay, so what that means is, if you look at it from an energy perspective, these ingredients are at a high energy level. Okay? And the products are at a lower energy level. And this energy difference is what's released. Okay, that's what you're doing. So you took ingredients from a higher energy state to products at a lower energy state, and the difference is what you released. Did you guys understand that? All right, so now let me put it another way. And there's a reason for me to do this. You guys remember this equation? Have you seen this equation?
Mm-hmm.
Where have you seen it?
Disney Channel.
Disney Channel. Okay. Who came up with this equation? Einstein. Yeah. Okay, so what this tells you is, this is energy, this is mass, this is the speed of light. Okay. This is the energy equivalence of mass. If you could convert mass into energy, that's how much energy you would get. So whenever you're releasing energy, you're converting mass into energy. Now, this is not easy to do. Okay. So for instance, you can go into that parking lot, take any one car. If you could convert all of that to energy, you could run the US for 1 year. Okay, so that's not an easy process. Did you guys understand what I'm saying? All right. So this is ingredients, this is the product. Anytime you released energy, that means the products weigh less than the ingredients. Okay? Now, it turns out that whenever you're doing chemistry, the energy released is very small. Now, let's say you mess with a nucleus, we'll come to this later. If you, in a nuclear reactor, which we'll see in, if you go to UF. So in a nuclear reactor, you take a heavy nucleus and split it into two smaller pieces. This weighs a lot less than this compared to this process. When you do this, you're releasing 1,000,000 times more energy per molecule. So when you burn one methane molecule, if you're releasing so much energy, you split one uranium nucleus, you're releasing roughly 10 million times more energy per molecule. What is the other benefit?
You don't have to burn anything?
No carbon dioxide.
There you go. Okay, this guy is the villain. What you want to do is get energy without releasing this guy. You guys see the crux of the problem? All right. So fossil fuels are hydrocarbons. We burn fossil fuels and convert the heat generated to electricity or mechanical energy. Okay. So fossil fuels are coal, gas, and petroleum. Okay. So it turns out that if you have more hydrogen than carbon, increasing H to C ratio, it has more energy content. Okay. And increasing H to C ratio also releases less carbon dioxide. What is it that you want? You want more energy and less carbon dioxide. Okay? So this shows you what is the best. If you're going to use fossil fuels, it shows you what is the best fossil fuel to use. Okay? Here's energy content per gram. That's kilojoules per gram. Okay. Hydrogen has a lot of energy. Okay. How do you get hydrogen? It's not a fossil fuel. There's no free hydrogen on Earth. Okay. All the hydrogen is gone away to space. But how can you get hydrogen? Hydrogen is a way to store energy. You can electrolyze water. All right, so if you can produce electricity using solar and wind, split water, and what did you end up doing? You produced hydrogen, so this energy got stored in there. Okay, and then you can use the hydrogen to run your cars and stuff like that. Okay? You can use fuel cells to run that, or you could produce electricity if you want for later use. Okay, so using electrolysis, you can produce energy in hydrogen, store energy in hydrogen. Anyway, so hydrogen has a lot of energy content. Look at this. This is natural gas. Natural gas has 4 hydrogen atoms to every carbon atom. 4 hydrogen atoms to every carbon atom. Energy content is that many kilojoules per gram, and carbon dioxide released that many moles per 1,000 kilojoules produced. So it releases this much carbon dioxide. Petroleum has 2-to-1 ratio hydrogen to carbon, and you see it's releasing less energy per gram, and it's producing more carbon dioxide per 1,000 kilojoules of energy released. So why do we use, natural gas is cleaner than petroleum, so why do we use petroleum? Why don't we use the lesser of the two evils?
Easier to use.
I'm sorry? Yeah, see, gas is more expensive to transport. Petroleum is easier to transport. Coal is even worse. See, the amount of CO2 released per 1,000 kilojoules of energy produced. Okay. All right, so we keep saying that you want to use an energy source that does not produce carbon dioxide. Okay. And if you release carbon dioxide in the atmosphere, what ends up happening is you're warming the planet, causing climate change. Okay, so let's see what's going on. All right, we are around because we have a source of energy. Okay, so the sun is providing energy, and because of the temperature of the sun, the light that comes in is visible light. Okay, and now if you, by the way, do you guys know how much energy you're getting from the sun? So here is a number you want to remember: 1,400 watts per meter squared. Okay. So here's a meter square. So if you take a meter square there, this is roughly a meter square, the size of this table. The amount of sunlight falling is 1,400 watt bulbs for every meter square. Okay. That's in outer space, just outside our atmosphere. Half of that reaches the surface. Okay. And the other half is reflected back. All right, so 700 watts per meter square is absorbed on the surface of the earth, by the way. So let me show. So here's the earth, and if you take this face, about 700 watts per meter square is absorbed. Okay, so R is the radius of the earth, and so this circular cross section, so pi r square times 700 watts per meter square. This is how much energy the earth absorbs. Okay, you don't have to worry about the formula. Okay, so we absorb that much heat. Now if you don't want the earth to warm up, then you have to radiate equal amount of energy. Now, if you were around in 1800, the amount of energy coming in was exactly equal to the amount of energy being radiated out. And the temperature of the earth was 14 degrees Celsius. Yeah. Now here's the crucial part. Okay. The light, well, here's an important part. The light coming in is visible light. The light radiation going out is infrared light. The property of the atmosphere is different for these radiation. And we're changing the property of the atmosphere. By adding the greenhouse gases, what it's making it opaque to these infrared radiation. So this infrared radiation is not easily escaping. And if the amount of energy radiated out is not equal to what's coming in, what will happen? And it'll get warmer. And in the last 50 years or so, 60, 70 years, we've been radiating less. Today, we're radiating about 3.2 watts per meter square less. And we're warming up the earth. Okay, so that number has been increasing over the last 50, 60 years. That's what the number is today. And the temperature today is about 15.5 degrees Celsius. So in 1800, it was 14 degrees Celsius. All right. If the total energy radiated is equal to the energy arriving, equilibrium is maintained and the Earth's temperature would remain constant. On the other hand, if the total energy emitted is less than the energy arriving, if the energy emitted is less than the energy arriving, the Earth will get warmer. All right, so here is the sunlight coming. The clouds reflect 20%, 6% is scattered, and so on. So 50% is absorbed by the surface. Okay.
Like 51% of the 700 watt.
No, 1400 was what was arriving here, so 700 is absorbed. Okay, but again, that's 700 watts per meter square of the flat Earth, but the Earth is curved, so on the average, that area is larger and so on. Okay, so it would be 700 watts per meter square if the Earth were flat and perpendicular to the sun. Okay. The rocks, soil, etc. re-emit this energy as infrared radiation. So we have absorbed this radiation, and when you emit this, you're emitting infrared radiation. What's coming is visible light, okay? And that's important because now the atmosphere behaves differently to infrared and visible light. Yep. Okay, so here's what happens. Infrared radiation is absorbed by CO2. Okay? And when you're radiating it, CO2 in the atmosphere absorbs it, and then it'll re-radiate it and gives warm some of the air, which will warm the planet. Okay? But it's absorbing it and re-emitting it in every.
It doesn't know what to do.
It's doing this. What? I wonder what that is. This has been happening in other rooms as well. I gotta talk to the network guys. All right, so infrared radiation emitted is absorbed by this CO2. It gives some of the energy to the air and warms it up, and then re-radiates some of the radiation. And it re-radiates in every direction, so essentially infrared radiation goes back and forth and gets trapped. And less energy is radiated. All right, so here's the deal. Okay, so for the longest time, we had the amount of carbon dioxide in the atmosphere was 280 parts per million. Okay, so you can think of it for the last 10,000 years. And with that much amount of CO2, the temperature was 14 degrees Celsius. Today, there's 420 parts per million. It's increased by 140, by 50%. And this is man-made. and the temperature has risen to 15.5 degrees Celsius. All right, well, we do need some CO2 in the atmosphere. For instance, if we had 0, by the way, what does ppm mean? What does that mean? For every million atoms in the atmosphere, molecules in the atmosphere, 280 are carbon dioxide. You know? What is in the atmosphere? Nitrogen and oxygen mainly. You know? So for every million nitrogen and oxygen molecules, 280 were carbon dioxide. Anyway, if you had no carbon dioxide in the atmosphere, this would be a cold place. We don't want that either. It would be a permanent ice age. We would have no oceans and stuff. Okay?
Already waking up to -2.
That's right. Well, you would have worse problems. I can assure you that. All right. So we need some. We don't need this much.
So the infrared radiation reacts with the
Carbon dioxide.
carbon dioxide. and
The
then-
carbon dioxide absorbs it. Yeah.
Okay. And then it will release it as heat reacting with the air, but it also releases it.
As the radiation, it re-emits the radiation, and that radiation bounces back and forth and gets trapped.
Because there's so much carbon dioxide, it doesn't get released.
Yep, it gets delayed. Mhm.
Okay.
Yeah. So here's a extreme example of this to make you understand. Okay. Do you guys know how far the Earth is from the sun? Hmm? Very good. This is called 1 astronomical unit, but it's about 100 million miles. Okay. Do you guys know how long light takes to get to Earth?
8 minutes.
Very good, 8 minutes. All right, so the radius of the sun is, this distance is 100 million miles. This is about 400,000 miles. Okay, you can look it up. Okay, so 0.4 million miles. A photon starting at the center of the sun takes 1 million years to get to the surface. Why? That's a short distance to travel. Hmm? It's getting absorbed and re-emitted, absorbed and re-emitted. Yep. So, all right. So anyway, this infrared radiation gets trapped, and eventually it'll get out. Okay, but in the process, it's warmed the Earth. Okay? To a certain extent, the greenhouse effect is essential for life. Without natural greenhouse effect, 0 carbon dioxide, our temperature would be minus 18 degrees Celsius. You don't want that. But you don't want 16 degrees either. Okay, so with 280 parts per million, we were at a comfortable 14 degrees Celsius.
And parts per million is per 1 million molecules, 280 of those are carbon?
Carbon dioxide, yeah. Okay, so that's the relevant number. Okay. Currently, the levels are 420 parts per million, and the temperature is 15.5 degrees Celsius. You want to be below 16 degrees. A few years ago, we were hoping to be below 15.5, but we've blown past that. What's that?
I said grade.
Mm-hmm. Now our goal is to be below 16. What happens at 16? Hmm?
Everything melts.
All of the Greenland ice sheet will melt irreversibly. And that's the belief. Okay, and that'll happen over a scale of, I don't know, maybe 3, 4, 5,000 years. So that's why it's so hard to legislate and stuff like that. But if this happens, what if Greenland melts, all of Greenland melts? Sea levels would rise by about 7 to 10 meters. 10% of the world's population would have to find new places to live besides extreme weather. 10% of the world's population is how many people? Almost 1 billion people. 3 times the US populations would have to move. So anyway, so that's the kind of problems you encounter. The concern today is that human activities through fossil fuel combustion and deforestation is increasing greenhouse gases in the atmosphere, leading to warming of the earth. Okay, so here's a graph. So this is around 1800. So that's this is the Berkeley Earth data prepared by Berkeley Earth. Okay, and you see in 2018-15 to 2025, we are about 15.5. So this is what this is 1800 is 0 degrees, which is 14 degrees. So they call it. Okay. And this is the temperature above that benchmark. Okay. So we've risen close to 1.6 degrees above the benchmark. So this would be 15.6 degrees.
What happened in the 30s, 40s that made it rise so randomly?
The war, I guess.
I suppose.
In the sense of like military and stuff like that. And
Yeah,
World
World War
stuff.
II and stuff.
Mhm. So anyway,
Anything
last 60 years, the rise has been almost exponential. Okay. And by the way, so how do we figure out the global temperature? We talked about this briefly. When they say the global temperature average is that, okay, so if you want to get the ground, so if you wanted to get the average temperature here, what you want to do is dig a hole this deep, essentially, about 4 to 5 meters deep, and measure the temperature in the ground there, and that gives you the average temperature at that location. Yeah? So let's say it's 15 degrees here, 14 degrees here, 12, and then you take the average over all the grid, and then you get the global temperature. Yeah? All right, so again, what we want is to limit the content CO2 in the atmosphere. Yeah. So you see this is a graph for the past 10,000 years. Look at this, in the last 50, 60 years, it's just gone up. Yep. So July 2024, it was 425 parts per million. So for about 10,000 years, it was steady at 280 parts per million, and then it's suddenly gone up. Okay, so this is a simulation for global temperatures and CO2 levels. Okay, so we are about here now. If the carbon content will be, or CO2 content is 430 to 480, the global temperature rise would be it can go as high as 3 degrees. So 14 plus 3, it would be 17 degrees. Okay, so these are simulations. And of course, if CO, hopefully we'll never get there. Okay, so let's say if it's CO2 levels are 500 ppm, the temperatures could rise by as much as 3.5 degrees. Okay, so what this graph shows you is the following. So if you were above our atmosphere is half our atmosphere is within 5 miles. But let's say you're 1,000 kilometers up, let's say, but you're 60 miles up from the Earth's surface. This is the radiation that is reaching us. What this is showing you is the intensity for these wavelengths. Okay? And the ozone is absorbing the ultraviolet light, which is a good thing. We're happy for that. And the water vapor is absorbing all of that. And we are emitting in the infrared radiation. So if we had no atmosphere, this is what we would emit. Okay. Water vapor is absorbing this radiation. Carbon dioxide is absorbing this, and water vapor is absorbing that. Okay. To a certain, we want a certain amount of carbon dioxide, so it absorbs this and warms the air, Earth to what temperature? From minus 18 to 14 degrees. We're happy about that. Okay. Now we're increasing the CO2 level, and we are absorbing more than we should. Or we are absorbing more than what we want. Okay, that's the problem. Okay, so radiative forcing, you want to understand this expression. So here are the incoming radiation, and here's the outgoing radiation. Okay, this minus this is the radiative forcing. If this was equal to that, then radiative forcing would be 0. Okay. When this is higher than that, you have positive radiating forcing and you're warming the Earth. Okay, so that's where the term comes from. Yeah. Radiative forcing is a measure of energy reaching the Earth minus the energy leaving the Earth. Okay. Earth has been in radiative imbalance since at least the 70s. So since at least the 70s, we've been radiating less than what's been coming in. Most of the extra energy has been absorbed by the oceans. Okay. So 93% has been absorbed. Well, how much is this? So because of human-generated greenhouse gases, there has been an imbalance of 3 watts per meter square. Okay. So what we are saying is, for every meter square is, like I said, this table of the surface of the Earth, we've been radiating 3.2 watts less. Well, so you add it up over all the surface of the Earth. Energy is being trapped on Earth at the rate of 1,600 terawatts. Okay. So now let me put this in perspective. 1,600 Okay, this is 16,000. This is a gigawatt. Does this number sound familiar? What is that number? Remember, that's the power needed to run the world. we're trapping energy at 100 times more energy than what's needed to run the world. All right, what does this mean? This is equivalent to exploding 20 atom bombs, the kind that were dropped on Hiroshima, every second, 24/7, and trapping the heat. That's how much heat we're trapping. What's that? Well, you can't do without it, but. Okay. So by the way, you have to be careful about this. There is as much as 12,000 gigatons of carbon in the fossil fuel deposits, coal, natural gas, okay, left today on Earth. So there's that much. This is carbon, not carbon dioxide. So carbon dioxide, so you would add the weight of oxygen to it. Okay? So, 12,000 gigatons of carbon. Current rate of fossil fuel burning is putting about 10 gigatons in the atmosphere each year. That's 10 gigatons of carbon. So if you wanted to calculate the weight of carbon dioxide, carbon weighs, there's carbon 12. Carbon weighs that much, and so for when you're putting one carbon atom, you're putting one carbon dioxide molecule, which is 32 plus 12, 44 atomic units. Okay? So 12 by 10 equal to 44 by x. So x is equal to 44 by 12 into 10. 622, 110 divided by 3, roughly 1838. So every time you put 10 gigatons of carbon in the atmosphere, that's the same as putting 38 tons of carbon dioxide in the atmosphere. Okay, so some people quote it in tons of carbon. We have dumped a total of 500 gigatons of carbon in the atmosphere since the Industrial Revolution. Simulations suggest that another 500 gigatons of carbon end up in the atmosphere, an amount that would require a transition off fossil fuels by the end of the century. Okay. So we are hoping that, but hopefully we won't even dump that. Okay, so all this will remain in the ground, hopefully. Yeah, so that's the best case scenario. Okay. If temperature rose by 2 degrees Celsius, what does that mean? If the Earth's temperature became 16 degrees Celsius. What's that? Yeah, so the time scale of complete melting of Greenland ice sheet would be that. Okay, if the temperature rises to 16 degrees Celsius, the irreversible loss of Greenland ice sheet is triggered. That's the belief. Yeah. The associated sea level rise would be 6 to 7 meters. These are conservative numbers. About 10% of the world's population live in coastlines less than 10 meters above sea level. They would all have to move. Yeah. Look at this. So this is how much energy we're consuming per second. Okay, so 16 terawatts. So to run the world, it's 16,000 gigawatts. 16 terawatts. That's what we need. Okay, you need 16,000 Hoover dams running all the time. This is a Hoover dam to run the world. Okay, or you can write it as 16 terawatts. That's what's needed. This is how much sunlight is falling on Earth. Okay, So 23,000 terawatts divided by 16 terawatts. So let me do that number for you. Okay, so 23,000 terawatt divided by 16 terawatts. What does that mean? What that means, what that number means, it's 1,400 or so. So think of these as pennies. If pennies are raining down, that's sunlight. For every 1,500 pennies that are falling, all you have to do is pick up one penny, and you can run the bulb. That's what that means.
Very efficient,
What's that?
very efficient.
And this is free. That's free. What we're saying is that's how much sunlight is falling on the earth. So why are we not doing it?
That's what I'm thinking.
Why aren't we doing it?
I mean, it's not complete.
Huh?
Depends on we have the technology to properly store it.
Storage is the problem. So you can run during daylight. What do you would do at night? You have to charge batteries, and batteries right now are expensive. That's the problem. Okay, so that's so if you want to be the richest person on the planet, come up with a cheap battery. Okay. All right, so anyway, but this is good news. So you can run the world on solar, you can run it just on wind, and so on. Okay, so you can run the world on renewables. Solar and wind each by themselves can provide enough energy to run the world. Currently, wind and solar are the cheapest source of energy. The bottlenecks for their widespread adoption are cheap storage and a smart grid. Okay. So the problem with electricity is you got to produce just the right amount, as much as you're using. So if you go turn off one light bulb, you have to produce that much less energy. Electricity. So if you cover these black dots with solar panels, you can produce enough solar electricity to run the world. All you have to do is cover those guys. Okay. At current solar panel efficiencies, 20%, 6 300 kilometers by 300 kilometers arrays of solar panels would fulfill the world's energy needs. Okay. All right, so this is a Stanford University study. I mean, this was back in 2012 when we were getting 80% from fossil fuels, more than let's say 85% from fossil fuels and renewables. Okay, so had that mixture been steady, if we hadn't gone towards renewables, what is the problem with fossil fuels? For every dollar, you're throwing 70 cents out the window. If that were true, in 2050, and again, this is undercutting because now AI is going to use a lot of energy, but anyway. So what they're saying is you would need 20,000 Hoover dams if you were running with the same mixture, 80-20 mixture. And what this graph is showing you is wind, water, and solar, WWS. So if by 2050 we switch all to renewable, the world could be run with 12,000 Hoover dams. And that's what that graph tells you. Yeah. So according to predictions by a group at Stanford University, By 2050, the world can be essentially be run on wind and solar energy alone. With current technology, you don't have to invent new technology. So you just have to put your mind to it. With current technology, you could run the boat. Okay. Also, the world can be running on only 12,000 gigawatts of electricity. Like I said again, this is a problem my generation has created, but it's for your generation to solve. So we're just telling you about the problem. Hopefully you understand and you're able to solve it.